Hello class, so this is CSE 5250, Section 2, Week 8. Week 8. We're halfway there. Living on a prayer. Right, so let's look back at the sieve that I had last week, and let's tie up a few less loose threads with the sieve itself. First off, let's recall that we can make a few optimizations with the sieve, such as for the outer loop, we can instead have it go up to the square root of the max number rather than the max number itself. And that's just an easy way of making the sieve run faster without any parallelism at all. So here's the outer for loop here in rank 0. And equivalently, we have the same thing for the for loop for all other processes. So that's the first optimization we can do. The second one's a little harder to explain, but the idea is when each bitmap is being received from all other processes, each process has only changed a few select bits in the bitmap, so we don't have to we don't have to compare every bit in the bitmap. We only have to compare the ones that each process has ever modified. So, if you look in the inner for loop for all other processes, you'll note that the for loop starts at a specific number based on that process's rank, and then it goes up by the com size -1. And those are the bits that one process will modify only. So we only need to consider those bits that are being modified when that process sends back that bitmap here. So here that bitmap is being received by rank 0, and keeping in mind how this for loop is set up, we can copy that and put it in here. So that way, this way we don't have to waste much time comparing bits that we don't have to compare. We'd only have to compare the bits that one process modified. Or at least would have modified. Because it's possible that it would have encountered a bit that it didn't need to flip to 0. But this is just to cover our bases. So, yeah. It's structured a little bit differently because here in this for loop, we've already used J, and I wanted to use K instead to keep us from getting confused between J and K. I can't use rank because that would equate to 0, so I'm using the J from this for loop to deduce the rank of the sending process. So for int K equals J would be the current rank from this for loop, -1. K is less than max number, and then we increment K by the com size -1. And we compared those bits only, not the entire bitmap's worth of bits. So that's one other optimization we can do. And if we run this thing, Control Shift B to build it, and move my face cam out of the way so I can show you where to find this thing more properly. Right-click the solution itself, open in File Explorer, move the window over here, put the face cam back, add some protein, debug folder. Wrong debug folder. It has to be the x64 one. x64 because it's a 64-bit machine. Debug folder for that. Type in cmd. And let's run it. MPI exec -n for processes and CSE-5250. And there we go. 2, 3, 5, 7, 11, 13, 17, 19, 23. All the way to 991 and 997. And rank 0 took 1700 microseconds to execute. Oh yeah. How do we time the execution time for this program anyway? Well, the easiest way to do that is to just... The easiest way to do that is to record the start time of the program right before we enter the for loop itself. We need chrono for that, so this is what the code looks like. Auto start equals standard chrono high resolution clock now. That will get the current time, and then we enter the for loop. And then once we exit the for loop, we enter the if statement, and then depending on which process it is, it enters a specific kind of for loop. And then when we're done with that, we can record the stop time after all of that, and then we can just print out the execution time. Now, I have already written this out, so basically what happens is this. If I just printed out only the execution time in microseconds, there's no I can't tell which process printed out what. So instead, I have it so that each process is printing out its rank and its execution time. So it basically reads, rank 0 took 1700 microseconds to execute. Ranks 2, 1, and 3 took slightly less time, and that's because rank 0 is basically waiting on ranks 1, 2, and 3 to look for prime numbers. No, cross out non-prime numbers and then send back that information to rank 0. Rank 0 is basically combining all that information into one updated bitmap that it can later send back to all the other ranks. So basically what I'm trying to say is, if you want to measure the execution time on this program, look at rank 0's execution time. Another way is to just have all this code be inserted at the very end of the code block for rank 0. So right after it printed out all the prime numbers, this is where you would insert it. That is another way, but if you want to be absolutely thorough, we can just, this is also another option. We just have all the processes report their execution times, but we only look at rank 0's execution time. Oh yeah. The working principles of how you record the execution time is simple. For the start time, we just record the current time, standard chrono high resolution clock now, and that's the start time. We execute all of the code as we normally would, and once we're done, we record the current time after that. So auto stop equals standard chrono high resolution clock now, and if you want the execution time, we just find the difference between stop and start. I'm storing that in a variable called execution time, exec time. So auto, exec time, standard chrono, duration cast, microseconds, stop minus start. And that's how we get the execution time for the sieve. This works with any other program that you might have if you want to measure its execution time. There's many ways of measuring execution time, but this one gets you this one has a resolution that's down to the microsecond. If you want something that can measure more precisely than just milliseconds. Alright, so onto the main thing right now is how do we get this thing to run if we want to search for even larger prime numbers? Because if I just set the max number to this, look what comes up. Function uses 3 million bytes of stack. 3 million? Yeah, 3 million bytes of stack. Consider moving some data to the heap. Now that is a warning that will come up with Visual Studio, and you could just ignore it, but when I tried it like that, the program wouldn't really run properly. See, it didn't print anything that time. So the solution to that, and I did get help from a student for this, the solution to this is to use dynamic memory allocation. So this is how it's done. We comment out the original initialization of the bitmap, and we instead initialize it using the star operator and the new we use the star operator and the new keyword. So bool star bitmap, and then on the next line, bitmap equals new bool, and then it's going to be an array with the quantity of elements corresponding to the max number. And now we can just use this array as we normally would, with a catch. We have to deallocate the memory when we're done. So this bitmap is the bitmap that contains this is the bitmap that rank 0 has to send and then later update and then send back to all of the processes. So once all that is done, we have to go all the way down here past everything else, and then we have to deallocate all that memory. That way we don't get memory leaks. So delete keyword, brackets, and then bitmap. That's how we delete the bitmap. That's one bitmap down. We have to do it again for all other bitmaps that we have in the code. So here, where we receive bitmaps from all the other processes, we can comment this out and see. I had already written this code ahead of time, and I'm just showing it to you now so we can see how it works. So comment that out. Add in bool star bitmap receive to replace this previous initialization. We say bitmap receive equals new bool max number, and then this bitmap is going to be used within this for loop, and once we're done with that, we have to deallocate all that memory. So delete bitmap receive. We're almost there. In the code for all the other processes, we have another bitmap, so we ought to comment that out, and then instead add in bool star bitmap, and then bitmap equals new bool max number. And then finally, we want to deallocate that memory once we've exited the for loop for that. So at the very end of the code for all other processes, we delete bitmap so we don't get memory leaks. And if I build this now, it should work now. Let's try it out. There we go. Rank 1 took 3.7 seconds to execute. Rank 2 and 3 took similar times, and rank 0 took a similar time. And there we go. That's the sum of Eratosthenes using MPI. If you've been following along, if you've been following along with these guides, you'll basically have the entire sieve up and running for the next phase of the course. And that next step is benchmarks. So the benchmark assignment is going to be your midterm assignment. We won't have a midterm exam. It's going to be a midterm project instead. Here we're just going to compare the performance of the sieve of Eratosthenes using the OpenMP and MPI sieves. We're going to compare performance based on different maximum numbers and different numbers of threads and processes. This is to simulate different workloads for parallel programs and different resources, different degrees of parallelism for the same program. So, your benchmarks will consist of 3 parts and they all total up to 120 points. The first one is the OpenMP benchmarks, the second one is the MPI benchmarks, and the third one is to answer a pair of questions. Which sieve do you feel was the easiest to implement and run? And where do you think the sweet spot is for performance gains? Another way to ask this question is, where is the point of diminishing returns, and at what point does adding more processes or threads make performance worse? I talked about Amdahl's law a few times during the course, but the thing about Amdahl's law is that it only considers the optimal theoretical maximum amount of speed up you'll get. It does not consider the overhead of context switching threads, or in the case of message passing, how long it takes to pass messages from one process to another. So basically, you'll be benchmarking the sieve that you made in programming assignments 1 and 2. I did not include NVIDIA. I did not include NVIDIA CUDA at all due to issues with trying to get it working in the lab computers. So once again, I've basically dropped that part of the course. But I would still like to show you what an NVIDIA CUDA sieve that's running. I still want to show you what it would look like. Just so we don't feel like we're missing out on anything. So, yeah. I've included a few example tables for you to get started, so for the OpenMP sieve, you have 16 entries for 1,000, 10,000, 100,000, and 1 million primes with 1, 2, 4, and 8 threads. For MPI, if you've been following along with how I programmed the sieve, we're starting at 2 processes instead because the single process, the one process case is basically the sieve, rank 0, is talking to no one and nothing is ever going to get done. So basically, the one process case will not work at all. So we have to start with 2 processes instead. And same thing as before, we're looking for primes out to 1,000, 10,000, 100,000, and 1 million. I highly recommend that you do trials for these, so run each sieve a few times for each combination of threads and maximum number. I say at least 5, but the more trials you can do, the better the results you get. And if you can, these tables are really just these tables are really a starting point. You are welcome to keep going and try primes up to 10 million, or if you have it, you can try even higher thread counts, such as 16 threads. Yeah, you're welcome to try that as well. You are also welcome to present your findings as a graph rather than a table. So a table, these tables are really for your convenience. It's really just a way of starting out with the benchmarking. So with that, I'm basically going to put out this video earlier this week so that you have the instructions on what to do for the benchmarks. I would like to make this assignment due maybe on the Wednesday of next week, just because you have ample time to complete the benchmarking. So yeah. I want to say that these benchmarks are due on next Wednesday. So that way you have ample time to do the benchmarks, answer the questions, do even more benchmarking if you want to, and then write up a quick report on your findings and what you think. So that's going to be it for this video. Have a good midterms week, and I'll see you next week.